Welcome. A quick update about the changes I'm going to make to System Devices 1. So, as always, I was looking through the internet and I came across this GitHub page with a VHDL HDMI out interface. So many thanks to Firkin Casey. Apologies about the pronunciation on that one. But no, thank you very much. This is a most excellent HDMI interface. I do confess I've always edged away from HDMI because I thought it would be scary. Not to say that I understand all the subtleties of how HDMI interfaces are made, but this VHDL description is very readable. So definitely it fools you into thinking you understand how it all works. But reading through it, yeah, it's a nice, well-described block of VHDL. So this opens up the opportunity to changing how the SYS1 module is taught. So it's always been AND gate to Pong. So it's always been AND gate to games console. So build your own games using the simple CPU. However, I do confess students never really got to the end of that process. By the time we got to a state where you could write your own game on the simple CPU, the open assessment had come out, and so focus changed from the teaching material to completing the assessment. So as you can see here, as the FPGA board we use in the lab has an HDMI output connector, this allows me to make some fundamental changes to how System Devices 1 is taught. So make it from day one games focus. So from day one, all the teaching examples will be based around game components, so graphics, interfaces. So the hardware we need in our games console so we can play games. So for example, if you want to introduce the concept of what binary is base 2, we can start to look at RGB, so the color space, red, green, blue values. So we can see how we can encode the brightness of our red and green components as binary values and actually visually see that on the screen using the HDMI interface. So send those color codes to the monitor in the lab so the students can change the brightness using dip switches or push buttons on the FPGA board to change the colors they see displayed. So I think this will work. I think this will allow a better understanding of how a computer architecture works because it's more hands-on, hopefully more engaging. So rather than trying to promote engagement with the promise of video games at the end, we have instant reward from day one. So we can make things flash on the screen within the first lab. So fingers crossed, touch wood, this is the way of the future. So if you go back and look at the VHDL, so if we look at the top level one, it supports different resolutions, all from HD all the way through to VGA. Obviously it would be nice to work in HD, but the downside is the frame buffer, the memory needed to store such images would be huge, and you'd have to implement that in the external DRAM on the board, which I want to try and avoid. I want to try and get everything in the FPGA. So I've had a play around, and yeah, if we go down to 320 by 240, everything is fine. The only if, but, and a maybe is HDMI does not support such low resolutions, but I can work around that one. So internally, we can work 320 times 240, and we can upscale to 640 by 480, your basic VGA. So that's all good. So working at a lower resolution, yes, means that the graphics are a bit more blocky, but the frame buffer, the internal memory is a lot smaller, and it allows us to have a wider range of functionality in our video controller. Out of the box, there's two examples. So you can have built into hardware a basic pattern generator, so generate some nice test images, and we have some hardware implemented graphics. So if we look at these ones, so the basic pattern generator, if we look here, it's a state machine, so we're going through changing the RGB values, so incrementing the green, decrementing the red, incrementing the blue. You can see so you're changing basically the RGB values so you get a nice pattern on the screen, which we'll see later. The other piece of hardware that comes with this interface allows us to draw some basic patterns, kind of comparable to hardware sprites. So this one doesn't have a frame buffer. Everything is directly implemented in hardware. So we declare our tile, our sprite, whatever you want to call it, and basic block shapes. So we have a ball and walls defined here. Your fundamental building blocks of Pong or something. But the key thing here is that these are not written into memory. You have dedicated hardware looking for when the pixels associated with these objects are being printed to the screen. So you can see you've got this decision-making hardware. Is the current X pixel position within the block that defines where that ball would be printed. So you've got the X and the Y pixel positions there that are examined through hardware comparators, and if the pixels are within your ball shape, then you'll print out onto that pixel a colour. Otherwise it will be black. And that's what you've got down the bottom here. You've got hardware sprites, if you want to think of that, hardware printed graphical elements. And again, these could be controlled by the processor, so their absolute position is determined by this input bus here. So you can pass to this function different XY positions to move the ball, to move your bat across the screen. So building upon this hardware, I've added some additional functionality. So inside the FPGA, I've defined a set of static colours. So you can see black, red, green, blue, yellow, purple, cyan and white. So they'll just set the whole screen to that particular colour. Then I have that nice test pattern generator. I've also added some memory, a basic frame buffer, so we can plot an image. So we can initialize that frame buffer with an image. So we can read in a JPEG and then initialize a ROM within the FPGA to store that image as a set of RGB values and then print that to the screen if that one is selected. Here we have our objects. Again, I've slightly expanded upon that one. So we can have different movable blocks. We can scale those blocks, and I've added hit detection as well. So automatically done in hardware, you can tell if those objects have collided. And finally, because we want to print out some text and some other tile information, exactly the same as my VGA implementation, I've implemented a simpler version of my hardware to draw tiles. So to see that in action, we can set the dip switches and see what happens. So 0 is black, 1 is red, 2 is green, 3 is blue, 4 is yellow. Confess this one, the white balance didn't like that. 5 is purple, 6 is cyan, and 7 is white. Again, the white balance didn't like that one. It honestly is white on the screen. I know the video makes it look like it's a grotty grey, but it is white, trust me. 8 is our nice test pattern. 9 is the image of Bob, stored in our ROM. This image again shows a design decision that I had to take. It's like, how many colours should this video controller support? So what is my colour depth? I decided to go for 2 bits for red, green and blue. So 6-bit colour gives me 64 colours in total. And for basic 8-bit games, I think that will be sufficient. But you can see here, Bob looks rather pixelated due to the limited colour depths. The shades of green that I can do are very limited. But I think it'll be sufficient for our simple games. 10 is our blocks. So this is basically just an expansion of the original core that came with the HDMI controller. So in this version, I have 4 blocks that can be any size. So you can see in the top left corner, you've got red, green, blue and yellow rectangles. So you can define the sizes from the full screen down to a 1x1 square. These blocks combined with the ball sprite that you can see in the middle, I think would be sufficient for most simple games. So as we saw, the ball sprite is defined within that component as a memory image, and they're 8x8 tiles. In addition to defining their position, you can also define a scaling factor. Scale by 1, 2, 4, 8, 16 or 32. You can see it's basically the same shape, just scaled up each time. And I thought that would be a handy addition. So you can vary the size of the image. I think scaling by 32 is a little bit too extreme. But yes, scaling by 2 or 4, I think that gives you some different shapes to play with. So in this component, the rectangular blocks are fixed at runtime. So you predefine their position and their size. So these could be the walls perhaps. The sprites, in this example, they're all balls, but they are just 8x8 tiles, so they can be any size and any shape. And these could be the bullets, balls, or players in the games. So in addition to the process of being able to define their XY position, so the top left corner, this hardware also does hitbox detection. So it will detect if any of these sprites collide or if they hit any of the rectangular blocks. So again, that moves some of the processing, some of the game logic out of software directly into hardware, which should help simplify the development of the initial games. Well, that was the 4 anyway. And 11 is our tile, a tiny space invader. So we can zoom in a little bit on there. Again, these are 8x8 tiles, and these are defined in a separate tile ROM. So in that we've got 2K bytes worth of storage, and we can store our ASCII characters and other useful tiles. Again, appreciation for the font characters that I again got from a GitHub release. So these define our ASCII characters. So you can see here our normal ASCII characters. We can print text on the screen and numbers. In addition to those, I added some graphical characters. So the graphics here are my interpretation of Space Invaders. So looking through here, we've got the different Space Invaders tiles with the different leg positions, so they can look like they're moving across the screen. I've also added some, here we've got a player for Space Invaders, some bunker tiles, the missiles, explosions, and some building blocks. So we can build some basic shapes, maybe the maze for Pac-Man or something. That's what the thought process was going on here. So some basic tiles that you can place on the screen. You define the XY position, so you define the position of the top left corner, and this hardware will draw those onto the screen. So you can see different shapes. And you can add as many as you desire for that one, just by expressing the 8x8 values. So you can see this shape here. It is defined by these 8-bit values. Each bit defines whether that pixel is on or off. So within this hardware, you have position registers, X and Y, and you have a color register allowing you to express that 6-bit color value. These tiles can only be one color to keep things nice and simple, but if you did want to have a multi-colored player, then you could overlay multiple of these tiles, and after each being different colors. And that's what typically was done in the early video games. Again, this is all implemented in ISE, so within this project now we have a simple CPU device embedded, and that allows you to write some code to define your game logic. Controllers, I'm not sure at this moment in time. We could add some Super NES controllers. I've got the VHDL for that one already written. Or we could just use the push buttons or the keypad on the FPGA board. So yeah, that's to be thought of. But yep, that's the direction I've decided to take SYS1. So moving away from the bug trap, I'm afraid. So no more squashing Bobs. We're going to build video games. Maybe Bob can make an appearance in that. But anyway, that's the future. I just thought I'd give a quick update on the direction I was thinking. As always, I will catch you next time in the labs.